afternoon, everyone. Welcome to our cozy room. My name is Ed Burns, and I'm going to be talking to you for the next 75 minutes, hopefully, about a topic that is interesting to me. Hopefully, it will also be interesting to you. And I'm glad that I'm not the last session before the happy hour, because that's always a tough thing. Everyone's wanting to get going. So you can do that to the next person. All right. Oh, you know what? I forgot to plug in my clicker. Let's see if this is going to work for me. Looks like it is. All right. Okay, I'm going to be talking to you about stuff that's still being developed. In particular, the Java SE9 content is literally hot off the presses. I just got it from the SE development team. They're talking about what they're doing with HTTP2 in Java SE9, and I have some slides and content on that that's not been released yet. So this safe harbor statement doubly applies there. Here's our agenda. My plan for how you're investing your time with me today. First, we'll cover why we need HTTP2 in the first place. If we've waited 15, 20 years already, why now? Can it wait longer? Some people think it might be able to wait longer. Some people think it's long past due. Let's talk about those various factors. Once I've established the rationale for why it needed to be done, we'll take a look at what are the big features in the HTTP2 protocol itself. And then, as a layer on top of HTTP2, which is what Servlet essentially is, how Servlet might expose these features. A little aside on Java SE9 support for HTTP2, and a little bit of a summary. So let's get right into it. This is a typical web page these days. You have, this is nothing unusual here, your web page plus a number of inline resources. And, when the IETF and the HTTP2 working group started, largely led by Google, they had access to terabytes and terabytes of browser data because it was Google after all. So they did a lot of research and surveys and analysis on the data that they had from being Google, and determined that on average, a web page has 30 resources. Well, actually, no. This particular web page here has 30 resources, 2 style sheets, 9 JavaScripts, 8 JPEG images, 2 PNGs, and a partridge in a pear tree. And it's a composite page, but it's also very representative of what's out there. So the first problem with this is what we like to call head-of-line blocking. Okay? So here's what head-of-line blocking is. This is part of what's in HTTP 1.1. It specifies that when the client makes a request to the server, it can certainly send the index.html GET request. The server responds with the page, and then the browser parses the HTML, discovers I need these follow-on resources. But the HTTP head-of-line blocking thing means the specification says the order that they're requested must be the same order in which they are served up. So let's say style 1 and style 2 come across quickly. No problem there. There's no server-side processing, for example. Because of head-of-line blocking, if the next resource gets stuck, the script 1, for example, takes a little bit longer, none of the other follow-on requests can be delivered until that script1.js is fully delivered. That's what head-of-line blocking is. So there's one thing that's standing in the line and preventing anyone else from going by it. So how do we work around it, right? A lot of what we have in the state-of-the-art of the web today is, you could affectionately call them optimizations, or you could more derisively call them hacks. But in any case, they're ways of taking what we have and making it go faster. And that's what web developers have been in the business of doing since forever. And they're a very inventive lot. They have come up with lots of different approaches to work around these different problems. Some of them were developed by page authors and website designers. Others were developed by browser vendors. So if the protocol itself has this property of requests must be returned in the order in which they are requested, responses must be returned in the order in which they are requested, what can we do to work around that? one thing browsers have done is just open up more sockets to the server. So nowadays, it's normal for a web browser to have 6 to 8 sockets open to any given server, any specific one given server. Now that doesn't mean there may be many different servers involved in serving this request. So you could have 6 to 8 sockets to each of them. So the browsers have become real big hogs of sending and consuming socket resources. So, but anyhow, that's the case, and we work around it by, the browsers work around it by opening up more sockets, and that way they can get more stuff from the servers to the browser faster. So, what are some of the other optimizations that we can do here? This head of line blocking problem, this socket reuse or socket usage problem. I'm going to talk about a few approaches that web developers have adopted. Specifically, file concatenation and image sprites, domain sharding, and the use of inlined assets. And to understand where this started, we got to go way back to this thing. Does anyone know what this thing is? This is where the problem started. And I can say that because I had a tiny little hand in it back in my college days. But prior to this, there was no concept of an inlined asset. So this just goes to show what can happen when you go from 0 of a thing to 1 or more of a thing. So making that jump from HTML was only a single page and there was nothing else inlined into it, from now the invention of the image tag. And of course, once you go from 0 to 1, it's not very far to go from 1 to more than 1. And then we started to get all of these other things that were coming along here. So the research that Google did when they were starting out the HTTP2 specification effort was that the modern web page now consists of more than 90 resources from 15 distinct different hosts. So let's talk about one way to work around this problem. It's this notion of image sprites. Has anyone heard of the concept of image sprites before? Okay, good. I'll go through it pretty quickly then. If you haven't, there's a very nice seminal article about this. Let me see, do I have a laser pointer? I do. It might not show up on my green screen. I feel like I'm looking at a VT100 with this green. All right, A List Apart is a really nice article. They're my go-to site for like the seminal articles on things. The responsive design, this image sprites, they just have very high quality stuff. Anyone familiar with A List Apart? And they also have a conference series called An Event Apart, which is really cool. I hope to go to it someday. Although, considering they don't have much to do with Java, I probably won't ever get to speak there unless I talk about something else. So what they want to do here is leverage the benefits of the TCP, the underlying network protocol that's several layers down from HTTP. And there's a part of TCP that's thing called the congestion window. And this is the thing that basically says, if the longer the connection is open and the more stuff you send down the pipe, the faster it will get. So they say, well, given that fact, let's just stuff all of our images into one big file and then use client-side manipulations to essentially move the little magnifying glass icon to show the image that you would like to show. And Sprites itself is a very old concept. If you've ever done any programming in the 80s on some of these old systems like the TI-99-4A that had a really nifty sprite system that I remember cutting my teeth on as a kid. So the concept is not new. Another trick is domain sharding. So I mentioned that web browsers only allow themselves between 6 and 8 sockets to any one given server. Well, if you're a hosting provider and you're aware of that limitation, we can say, well, I can play stupid DNS tricks and make the browser think that it's actually talking to different servers, when in fact it's just a virtual host name all going back to the same server. So with this approach, you can work around the browser-imposed limitation on how many parallel connections there are to a single host. Okay. Finally, we have the concept of inlined assets. Now, base64 encoding will never die. This goes back to the way it was before Mosaic came along, where it's just a single resource. So on the plus side, you get the benefit of the TCP congestion window benefits. But on the minus side, the images can't be cached. They can't be shared between pages that are similar. And then there's also this unnecessary base64 decoding that the browser has to do, which is not exactly the most size-friendly protocol, right? I mean, image formats, JPEG, PNG, they're optimized to be small. They are lossy in their compression algorithm, but they're good enough for the web, and most importantly, they're optimized for being small and easy to deliver. So when you base64 encode something, you don't necessarily lose that compression, but it just kind of fans out with the base64 encoding of it. So a quick show of hands here. Who has used any of these approaches in practice? Okay. And did you at any point find yourself saying, why in God's name do I have to do this stupid stuff? Yeah. Okay. Well, this is the kind of pain that the HTTP spec working group has been trying to alleviate. But this also poses a challenge in terms of adoption, because after, as I said, 15 or so years of all these different hacks upon hacks upon hacks being built up, there is an enormous body of prior art and websites out that are using these approaches. So to unwind that, you really do need to think differently about how you're going to be authoring your sites if you want to optimize for HTTP2. That's a topic for another session. Perhaps that will be my ticket to an event apart. Come up with something about that. So those are some of the problems. Let's now talk about the big features. Now we have 75 minutes here, so I decided to put in a little bit of an aside of network programming review here. And I think it's important, since HTTP2 is the first revision of the spec in forever, to look at the foundations a bit more before we go into what's new with the servlet exposing of it. So this is important because HTTP2 is essentially a new transport layer underneath the existing HTTP1 specification, plus a little header compression specification that kind of sits along the side of that. Thankfully, it's the same request-response model. It's the same set of HTTP methods. They aren't introducing any new HTTP methods. REST is still REST. They're not adding any new headers, really. They have new names and concepts for these the same old headers, but they just, most of the time it's the same name. Sometimes it's a slightly different name. Sometimes they're giving a slightly different twist on what that means as far as their protocol goes. So there's no new usage pattern from the application layer. It's the same usage of the URL spec and same usage of TCP ports and all that stuff. 8080, or not 8080, but 80 for ASCII and another port, 443 or so, I think, for SSL. Much more about that later about SSL. It's one of the most contentious topics in the HTTP2 world, is what to do with and how much to depend on SSL. But thankfully, they are really standing on the shoulders of the specifications that have come before. They're not, care has been taken to avoid the not invented here syndrome, I think. And that's very commendable, because when you're given the charter of, here you go, invent HTTP2, it's very tempting to say, oh, great, now's my chance to put my mark on the world. Well, that may be so, but they did so in a way that's very much respecting what has come before. So let's dive into this network programming review a little bit. Anyone familiar with this book? This is an old book, but very classic book that I'm fond of, Stevens' Unix Network Programming. And in that book, he has a little diagram, which is the 7 layers of the OSI protocol stack. And let me take a moment to review this. At the bottom level, you have the physical layer, which is your electrical connections, how to represent a 0 and a 1 on the wire. Next level up, the data link layer. This is where MAC addresses come in. This is node-to-node transfer, a direct connection between two machines on the network with no intermediary in between. The next layer up, layer 3, we have the network layer. This is where routing comes in. For example, the concept of datagram is introduced at the network layer. And this is where we say how datagrams make it from one node to another through one or more intermediaries. This is where multicast group management, joining and leaving multicast groups, comes in. Now we're getting to the place where we start to know a little more about things, more common. At the transport layer, this is where TCP and UDP lives. We're still not to the level of socket yet. Socket comes in at the next level, the session level. This is the home of the concept of a connection being able to be opened and closed and stay open for some amount of time. That's where the Unix socket API lives. The presentation layer, this is kind of oddly where the transport layer security lives, TLS, SSL, it's called TLS, but it lives at the presentation layer of the stack, even though there's another layer called transport, so that's kind of funny. MIME, Multimedia Internet Mail Extensions, is another level 6 technology. And so that's the quick review. Does anyone here have anything to do with layers 6 and below at all in their day job? Okay, all right, so that's nice. The web developers, because the web is an application, HTTP is an application protocol, so you can see it comes out at the application layer. But HTTP2 adds a number of concepts that are kind of analogous to some of the other layers in the stack. So it introduces the concept in the protocol of a connection, and on top of that you have in the HTTP spec a concept of frames and also a concept of streams. And finally, on top of all of that, again, all of this happening in layer 7, you have the HTTP 1.1 semantics that we all know and understand and have been using for a very long time. Now that I've established the foundation of network protocol here and the precedent for standing on the shoulders of others, let's take a look at the socket angle again. So in HTTP 1.1, sockets are kind of seen as a throwaway resource. The HTTP 1.1 spec says nothing about how sockets are to be used. Browsers are free to open as many sockets to the server as they like. This rule about how many parallel sockets may be opened is really a gentleman's agreement. The original NCSA Mosaic that I mentioned before only opened, let me get my bag, only opened one socket to the server at a time. And I remember when Internet Explorer came out and they, God forbid, opened 4 sockets simultaneously. People started calling it Internet Exploiter. Does anyone remember that moniker? It's pretty old. Now, HTTP 2 says a whole lot about how sockets are supposed to be used. They're seen as a scarce resource. The specification only says you're supposed to have one open per server. So again, if your website's already using domain sharding, then the browser has no chance of being able to discover that these multiple sockets are actually going to different sites. So this is one example where that particular optimization needs to be completely redone in order to get the most out of HTTP 2. So coming back to, this is the first time in the talk I'm going to specifically mention Servlet. What they've done with HTTP 2, it would be similar as if we took the existing Servlet specification, where you have a Servlet container, and the Servlet container calls into your Servlet with a service method, and then you do some stuff in your service method, and then you return. It would be similar to if we, in the Servlet spec, added another layer beneath Servlet and put it in the Servlet specification, and then defined it underneath what was existing there. But we're not going to be doing that. We have some different approaches that I'll talk about. Much more conservative. Servlet is a very old technology. I like to say that I still work on JSF, which is also an old technology, but I exchanged one old technology for an even older one. So I don't know if that's a forward move in my career, but it's something different anyway. This picture I showed earlier with the socket angle, we're showing how all of these different sockets that we had before are now kind of being combined into one connection, and then you have a lot more going on in that one physical connection. Now that I've covered the socket angle, I want to talk about the adoption angle. This is a different layer of concern, but an important one. When HTTP 1.0 first came out, it was designed to be easy to implement with contemporary development practices of 1991. So it was a text-based protocol. It left flow control entirely to the TCP layer. It said nothing about that. Easy to write a parser, it's text, you can look at it. It had a very simple socket lifecycle, open, close, nothing fancy like that. HTTP 2, on the other hand, is much more complicated to implement. So I think it's important to point out that there's a lot to be said with starting simple. I mean, there's a lot of the ideas here, as you can see, go back a long time to the 1960s, some of these ideas. So it's not like when HTTP 1 came out, they could have done something this complex, but they made a conscious choice to keep it real simple. And that's hugely important, because if they didn't do that, I don't think things would have taken off with the explosive growth that they did. I mean, it had to be easy enough that a college kid like Rob McCool could write the NCSA HTTP server and sort of take off from there. On the sad side, though, with HTTP 2 being a binary protocol, and I'll talk about what that is next, there's no more telnetting to port 80 and issuing a GET request with your typewriter keys and carriage return line feed, carriage return line feed. So I'm going to pour out a 40 for that and a moment of silence. So now we've covered the foundations enough. It's time to get into the big ticket features a little bit more. Much of what I'm saying here is covered quite well in the December 2014, maybe even 2013, issue of the Communications of the ACM. Any ACM members here? I highly encourage you to join ACM if you're a computing professional. It's a very good resource to have, and so do check that out. However, another option for getting the same data is this nice book by the same author of that article in the Communications of the ACM magazine, Ilya Grigorik. He's a developer advocate at Google, and he works with the team that was doing the HTTP 2 spec at the IETF, that is. You can find a free online copy of this book by searching for high performance browser networking. So it's a very good read. All right, it lets you do more with a single TCP connection. That's a feature that they call request response multiplexing. So it's a fully bidirectional communications medium between the server and the client and the server. And this is enabled by defining some terms. So the connection, as far as the H2 spec goes, is a TCP socket. The stream, bless you, is a channel within the connection. A message is a logical message, such as a request or a response. And a frame is the smallest unit of communication in HTTP 2. Represented graphically, it kind of looks like this. So you have one connection, and in it you have one or more streams, and within each stream you have one or more messages, and within each message you have a number of frames. So once you split the communication up into these frames, you can do this request-response interleaving. And this is how you're able to get a lot more parallelism with a single TCP connection, by basically defining semantics for how these units of message are delivered. One interesting little expedient that they defined is the notion of a stream ID. So all stream IDs are unique within the scope of a connection, but all the stream IDs originating from the client are given odd-numbered stream identifiers, and stream IDs originating from the server are all given even stream IDs. Another thing to point out here is you can see we have the server is responding with headers and then data. So headers always must precede the data that they're related to. But the data itself, can be broken up into any number of frames. And in fact, there can be more than one headers frame as well. They use a thing called a continuation frame when they want to, when it's not possible to fit all the stuff within one frame. So while we are sending down stream 2, and we're starting with stream 4, we're sending up another request stream 7 headers and data, and then stream 9 headers, and we assume the data will be following there. So once we dumped the ASCII protocol, we had to define a binary protocol, and this is the basic diagram of what a frame is. You have 24 bits of length header, followed by 8 bits of a type header, then 8 bits of a flag field. The flags let you basically set options that apply to this frame depending on the type. So for each frame type, there are a number of options that can apply. There's one reserved bit there. Then the stream identifier is represented as 31 bits. And then finally, the frame payload. Okay, so the length shows how long the entire frame is going to be, including the frame payload. So let me just quickly go over the different type fields. The basic two that are most important is data, request or response body. Headers being the request or response header. Reset stream. This is used when when the server is going to be trying to do a server push, but the browser says, no, I don't want this push. I'll talk more about push later, but basically RST stream means reset stream, and it's something that is used to say, let's cancel this particular stream. Whatever you're going to send me, I don't want it. The settings frame allows you to send configuration data that applies to a given stream, such as setting the priority, for example. Okay, and the size of the header table is another thing that we deal with there. The push promise frame. This is an important one, which really is the biggest of the big ticket features in HTTP2, and I'll talk a lot more about that later. And I believe we'll have time even for a demo. I think we're going quite fast. What are we on now? What slide number is that? 40. Yeah, we're definitely cruising along here. Okay, there's a ping frame, which this can be used to assert that the connection is still live. And in fact, the specification talks about how often ping frames need to be sent, because when you're going to have the connection open for longer, there has to be a way to make sure it's not closed. Now, one of the challenges that they have to deal with is intermediaries, such as proxies. So it's a big problem because a lot of times the proxies will not be HTTP2. So if you're connecting and your browser is HTTP2 capable and you're connecting to a server that is also HTTP2 capable, if the proxy in the middle is not, then you're not getting any of the benefit. So these frames have to be able to go all the way through in order for the benefits to be realized. Okay. I mentioned one other one, the continuation frame. This is an important frame that's used all the time when the size of a given frame is less than what needs to convey the actual semantic that needs to be conveyed. So the top #1 goal of HTTP2 is just to make the browser experience, user perceived browser experience, faster. That's the main thing. And that was, this being Google, they're all about page load time. And they invested all the time and effort in that. So I talked about the socket reuse. Another important thing they've done is header compression. Now, this is born of a really interesting and kind of obvious observation. Most of the headers are the same in a given stream. So with HTTP 1.1, you're sending the host and accept header, and you're sending a lot of the same stuff every time. So given that that's a lot of wasted bandwidth, why don't we come up with some way to not have to send that? So, again, this is introducing a state machine that now has to reside on the server and the client and be kept in sync. So what they do is they have these two tables, which are data structures, that reside on the client and on the server, and the specification defines how these header tables are to be updated. So instead of sending all of the headers, it basically sends deltas saying, change this one, but all the rest stay the same. So I have some examples to explain what that means a little more. I want to stress again, though, the complexity of this was one of the most controversial aspects of the HTTP2 working group. Some would argue it's overkill. We don't really need it. Another factor to consider when looking at the simplicity of H1 compared to the complexity of H2 was when H1 was developed, the web was not the only distributed information system game in town. Back then, there were other things such as Archie and Gopher and Waze. Has anyone heard of any of those? Right? So back then, people thought, well, it might not be www. Gopher might be the protocol that rules the world. So again, simplicity was important. But now that the web has won, and HTTP has won, we can pour on the complexity. Plus, the set of people that need to write a browser or a server is much smaller than it was back then, because all of the consolidation has happened. Who here has heard of SPDY, S-P-D-Y? Okay. Now, SPDY is a protocol effort defined by Google that largely was the basis for HTTP2. One thing that SPDY doesn't have, that HTTP2 does have, is this header compression algorithm thing. SPDY just uses a simple zlib compression of its headers. So you're still sending all those extra bytes for the repetitive header things, where HPAC, which I'm going to explain next, does a lot better job. Excuse me. All right, so on the left side we have the HTTP 1.1 representation, and on the right, the same thing, how it would be represented textually as HTTP 2. Remember, HTTP 2 is binary, so you're never going to see colon method colon. This is just a representation that's human readable. So here we have get index HTML, HTTP 1.1. We're sending the host header and we're sending the accept header. So this entire HTTP request in H2 is represented as a headers frame. So in this little notation here, the plus means add this header to that shared table that's maintained both on the client and the server for that specific connection. Colon method colon, that is what's called a pseudo header. These are the pseudo header fields. They're special header fields defined by HTTP2 that hold information that was formerly on the request line or for other must-have HTTP headers. And these pseudo header fields must end with a colon. Okay. Also, the header names themselves must be in lowercase, but the strings are compared using a case-insensitive fashion as far as the char set of the string comparisons goes. Another example. This is the response. In this case, the response fits into two frames. We're subtracting the end stream header from the table, which was added in the previous one. We add end stream. Now we're saying remove the end stream and add an end headers frame. Here's the status pseudo header field. We're specifying the content length and the content type as headers. And a second frame, adding the end stream, and here are the bytes of the response, hello world. Okay, that's HPAC. Keto, question.
Those values like end stream and header, are those just bytes?
Those are represented as type fields. Those are stream types, yeah, in the binary frame representation. It's a kind of frame. Okay. Another important feature is stream prioritization. We realize there's a lot more going on in the connection, so why don't we make it so the browser can make some intelligent decisions about the priorities of these things. And this is how stream prioritization works. It's defined in a headers frame or a special priority frame. It provides an additional 40 bytes, including the stream ID, the weight of the priority, 1 through 256, and it's because 8 bits, of course, and an exclusive bit. And I'll talk about that. Now, I say only a suggestion because the browser is free to ignore what the server says as far as priority goes. It's only advice. Okay? So the idea is we have three streams here, A, B, and C. So if A seems to be stuck for some reason, but we already have other streams B and C happening in parallel, these priorities say that the attention that you give to these streams should be distributed at a ratio of 4 to 12. That's what that means. So it's a way to allow the browser to pay attention to advice from the server if it wants to. So it should give more attention to C than B in a ratio of 4 to 12. Now I mentioned the exclusive flag. That allows for an insertion of a new level of dependency. So if the exclusive flag is set, here we have three streams, four streams rather, A, and then beneath it we have B, D, and C, distributed at the ratios of 4 and 16 and 12. And there's no exclusive bit set. But if stream D does have its exclusive bit set, then that means that it has the exclusive dependency on A, and B and C are now moved down below. So if A is blocked, then focus on D. If D is blocked, then focus on B or C at the ratio specified there. Okay, next we come up to server push. This completely eliminates the need for resource inlining anymore. Because with resource inlining, as I mentioned earlier, you're putting the image in the same request as the HTML page. Well, now you're essentially getting the same thing, but the server's handling it for you, which is nice because then you get the benefits of caching and all that other kind of stuff. It's basically a facility for the server to pre-populate the browser's cache with data that it knows the browser is going to need anyway. Okay? Now let me clear up any confusion on this before we begin to get into more depth. Let's see here. This is not a replacement for server-sent events, because server-sent events is an application layer thing. You know, it has a JavaScript API to it. This is strictly a protocol layer thing. However, one approach you can do for this is do some server push to pre-populate the browser cache, and then use a server-sent event to tell the browser to go and fetch this thing, but the server already knows it's in the cache because it's been pushed there. That's kind of how server-sent events might fit into this picture. But generally, you don't even need to think of that as far as server push goes. And I'll get into this in more detail when we talk to the Servlet API of it. Question?
My question may be answered later on, but I've implemented Speedy with server push on JD9, and one of the issues I ran into when you say server push, but you don't have to really think about it, is we push data even if the browser has it cached.
Right.
Because we don't have that, you don't know, unlike page speed from Google, you don't know whether or not that particular instance is cached or not.
Right. Right. Well, that's the push promise frame, which is sent ahead of the actual pushed bytes, is the facility for the browser to say, no, I don't want that. So when the protocol says that when the server is about to push, it's to send a push promise frame, which is essentially the server saying, hey, I'm going to give you this. And it's kind of a vague thing in the spec, but I think it says the server, if the server doesn't respond with an RST stream within a reasonable amount of time, then the server may commence sending the push bytes. So the way we work around that, or the way they decided in the spec to work around that, is do an RST stream on that stream. So, and that says, no, I don't want it. Sure. Any other questions? Okay. Another factor is this HTTP2 upgrade from 1.1. So the question here is it going to be secure or not secure, right? So if it's not secure, we do indeed use port 80 or by default and use the existing 101 switching protocols HTTP 1.1 facility. However, the big push has always been with HTTP2 to make everything SSL everywhere. And I'll talk more about that later. But when you make that decision, you can push on, that's the wrong word, you can offload the decision of protocol negotiation to a lower level thing. So there's a lower level spec called ALPN, Application Layer Protocol Negotiation, which is basically kind of a newish version of SSL. And there is some stuff in there that lets the client say, hey, I support H2. Do you give me H2? And the server can say, yes, I give you H2. So it lets that negotiation happen at the SSL layer rather than using the 101 switching protocols thing. Okay. Now, there's been a lot of criticism about this thing. And these are just a few of the things that I came across when the working group, I'm not on the HTTP working group. That's beyond me. Those are some really smart folks, and they, God bless them, they've been doing a great job. But some of the criticisms that were levied when they went to working group last call include head of line blocking is still a problem. It's just shuffled around. And that's because head of line blocking can still happen in the headers frames. The headers frames still have to be ordered in the same way that they always have had to be. So the concern is servers, being smart, might choose to put more data in the headers to get around these problems with priority and such, and kind of get back to the same problem we had before. So I would argue personally that that would be a misuse of the protocol, but the people in the expert group that were objecting on these grounds were basically saying, well, you know, clients are just going to do whatever they can to get the most performance out of it. So that was a concern. Another big problem was Firefox and Chrome have decided that there is not going to be any plain text HTTP2. So if you're doing HTTP2, it's always going to be SSL based. And this is one of the most controversial aspects. And this is kind of really fun, I think, because it touches on a lot of the hot button issues of our time. I mean, where else in the IETF world can you invoke Snowden other than here? So IETF had this thing, IETF RFC 7258, which the title of which is Pervasive Monitoring is an Attack. And in that RFC, they said to, hey, if you're developing an RFC, you need to put in the protocol things to make it hard for the government to do pervasive monitoring. And so HTTP2 said, well, how are we going to interpret this? We're going to interpret this directive as, you know, well, you can do HTTP2 over TCP if you want. It's in the spec, but we're going to say the two most popular browsers, and I'm not sure where Safari fits, whether they've decided on this. Does anyone know if Safari is going to support TCP clear text HTTP2?
Not today. At least they're moving from Speedy to HTTP2, and in doing so, it looks like they're all embracing, at least 75% are embracing HTTPS.
Okay, all right. So that means the big three, but interestingly, IE, Internet Explorer, has announced they're going to support non-SSL based HTTP2. So they're bucking the trend. I guess they're more friendly to the government, I suppose. So anyhow, H2C is the ALPN protocol string that means clear text, non-encrypted communication. H2 is the normal encrypted kind. Another complaint that was levied was, well, we're doing all this header table manipulation here, and that's going to take a lot of processor time that we wouldn't otherwise have to do. So some people have said the carbon footprint for all that HPAC encoding and decoding. One thing that I've observed is just with so much new spec language in this technology, it seems to me there's quite a lot of new attack vectors for denial of service attacks to be invented. So I think this is going to be a hacker's field day. Another complaint was that HTTP2 doesn't do anything for WebSocket. It's pretty much completely orthogonal to WebSocket. Personally, I don't think that's a complaint because WebSocket is an application layer thing with a programming language API, a nice JavaScript affordance you can use, and HTTP2 is a lower level network protocol thing. So I don't worry about that. If you're interested in a fun read of the criticism here, You can see this guy Polhenning Camp. He's the guy who was behind the Varnish Varnish HTTP accelerator. He's on the working group, and he posted his list there. Question?
Yeah. What was the final decision on the secure proxies?
I don't know. I'm not familiar with that one.
Okay, they were talking about in order to be able to cache, if you're encrypting everything, they can't do it locally. So you would connect to a proxy, it would cache it there.
Right.
And basically do a man in the middle.
I have read about that, and I think the current thinking was they're just not going to cache. It's got to go end to end, not cacheable.
Yeah, you can only cache at SSL termination points. And we deal with schools, and that's exactly what we have to do to support Speedy, and ultimately HTTP2 will be your Barracudas, your all those man-in-the-middle devices will have to support the higher protocol, but there's still going to be the SSL termination point.
So if you want, I've uploaded my slides to SlideShare, and they're also going to be on the conference website. So if you want to follow this link, we cross-posted it to the working group and also to ACMQ, another great ACM resource. The funny thing about this article was, in the same sentence, he mentions Taylor Swift, Ronald Reagan, and Samuel Beckett in ranting about the problems with HTTP2. So it's worth a read. He's an interesting guy. But don't take my word for it. Check it out yourself, right? HTTP2 isn't one spec. It's really two specs built on top of many other specs, right? So you've got the HTTP2 RFC. Now, it's been delivered to the RFC editor. We're waiting for them to give it a number. I don't know what number it'll be. But it references RFC 7230, which is the HTTP 1.1 messaging, RFC 4648, base 64 encoding, RFC 7323, range requests, 7231, HTTP 1.1 semantics and content, and so on and so on. There's a lot to read if you want to get to the bottom of this. Or you could just use Servlet, which sits on top of all this and provides a nice, easy-to-use API. And this gives me a segue into a little aside here about servlets and reactive programming. We okay so far? Okay. So this is the reactive programming diagram. Has everyone seen this in some capacity? Well, let me explain it briefly. The notion is you've got these four concerns here, and they're related with the ways the arrows go. Responsive meaning it responds to user requests in a timely manner. Resilient meaning it can withstand outages with graceful degradation. Elastic meaning the system response is not too heavily degraded when demand is high. Resource utilization is not too heavy when demand is low. It is message driven, meaning it allows the parts of the system to be loosely coupled and interact with each other in an asynchronous manner. So we've paid attention to this. You may have seen these banners. We are reactive. Everyone has to have a banner if they're doing something cool. So Servlet can proudly wear that banner, but it really only concentrates on two of these concerns, responsive and message-driven. And I'll talk about what that is, how that applies actually. Responsive and message-driven. That's what I mean when I say Servlet is reactive. So one problem with the We Are Reactive banner is that it's very hard to proudly wear that all the time, right? So the instant you have to block for I/O, you are no longer reactive. And that's true at any layer of your stack. So it's a very rigorous thing to say you have a reactive-based system. So from the moment the interaction enters your system, all the way down to the database and beyond, if there's any kind of blocking that occurs, then technically speaking, you're not reactive. My main purpose in saying that Servlet is reactive is that it's possible to entirely avoid blocking if you are really careful. So it's possible to be reactive. I guess we could have a banner that says, we can be reactive, not we are reactive. But I really think that none of these people that are saying they are reactive are truly like non-reactive proof anyhow. So what we do in in Servlet 3.1, we added these new APIs here. Read listener, we had an is ready on the Servlet input stream. Likewise, on the output stream, we added set write listener and also an is ready method. Within the read listener and write listener, we have these on data available, on all data read, on error. and write listener. So these were all added in 3.1 to basically let you do non-blocking I/O. And it makes it possible to do reactive programming with Servlet. 3.1 was the version of Servlet that we shipped in Java EE 7. And 4.0 will be the version that's in Java EE 8. But we didn't start in Java EE 7. Even in Java EE 6, we had some asynchronous there before the Reactive Manifesto came out. We had the whole concept of async. So with async, you have the concept of saying to the servlet request, start operating in async mode. And then once you're in async mode, you can add listeners, do dispatches, and indicate completion. And the async listener has these methods on complete, on error, on start async, on timeout. These are the reactive affordances in the Servlet API. Now I've put server sent events here. Even though there isn't any specific API in Servlet for server sent events, it's actually very easy to do. We discussed in the expert group if we needed to add some API, and the conclusion was because it's such a trivial thing to do with just server sent events natively, we decided to not bother putting it in the spec. It would just add complexity. So you can do it. There are some blogs out there. If you just blog search Servlet SSE, my colleague Xinghai Chen, who is the co-spec lead for Servlet 4.0, along with me, has some good blogs about doing that. Okay, we've got 25 minutes left. Yes, Reza?
Okay, so might have a reactive Java EE talk tomorrow after noon. I'll be talking about.
What time is it at?
I believe it's at 1 o'clock-ish.
Okay, so Reza has an excellent reactive Java EE talk. We'll be talking about the APIs that I've shown here, and do attend that. So we've covered in quite some good depth what these features are. Let's now talk about how Servlet might expose these new features, right? And this is an interesting choice because there's a lot in HTTP2, as I've illustrated. The question is, what does it make sense to expose to the Servlet API layer? The first big challenge we have to face is the existing Servlet API is designed for one request, one response, right? And HTTP2 being bidirectional kind of destroys that assumption. So it's going to be challenging to do justice to that, but I think we have a way to do it. And but we must not simply bolt the one or more responses concept onto some convenient part of the existing API. It could be argued, when you look at how we did asynchronous in Servlet 3.0, it was really kind of a bolt-on type thing. We introduced this new mode. So you have to be aware when you're programming, am I in async mode or not? Because all of the API methods that you can call in async mode have slightly different semantics if you're in async mode versus if you're in non-async mode. So that's a tricky thing, and we might, I don't think we'll have to do that kind of trick to do H2, but we'll see. So this is our list of features in H2, and really these are the only ones I think we need to expose. So what might that look? Adding the stream ID to the request and response, that's pretty simple. Adding a priority, so being able to access and set the priority on the outgoing responses, and being able to interrogate the priority of requests coming in is something we want to do. So we would add a priority class. It's important to note that this is not just a simple integer, as I've mentioned before. The priority has this weighted thing that you have to calculate. It might be helpful to add some API that lets us take those ratios and give you something easier to program with as well, so you don't have to do the math yourself. That might be handy. Now we come to server push. This is where I think the most accessible feature is. The idea is to push a resource to the client for a given URL and headers. And you may add a callback for the completion of an error or a push. Again, it's not a replacement for WebSocket. And I think it's really useful for frameworks that build on top of servlets, such as JSF. So here's how that would look. You have your browser issuing the GET request. You have your server, which gets its service method invoked. The server discovers, hey, when I'm processing this HTML on the server side, if you're a web framework that is, it discovers the browser will need these two resources. So it could do a dispatch push request for both of those things, which would basically be a synthetic GET to itself, which would be invoked on a separate thread, again, for each one. And those separate invocations of service for these follow-on resources would start sending their bytes to the client before the server sent down the index HTML. So there's two basic ideas for this. Web frameworks such as JSF, but not the only one, have this a priori knowledge of what resources go with what pages, because the page author tells you that. When you're coding your page in JSF, you have some syntax to say this is a resource that I want JSF to handle. So the minute you tell JSF this thing is a resource, JSF knows, okay, this resource is going to go with this page. So it can start and do the push that way. The other way that is not web framework specific is using some kind of heuristics. And this is what Jetty does, and probably what Glassfish will do as well, where it builds up a cache over time of which resources the browser requests after getting an HTML page request. So it basically learns as it goes and establishes the mapping that index page includes these follow-ons, and address page includes these follow-ons. And so it builds a table as it goes along and gets faster and faster. So it warms up and gets faster. So let's take a demo real quick. We got about 15 minutes left, and we still have to cover the SE9 stuff. But I think we're in good shape. So this is the stock Faces servlet. Who here has used JSF in some capacity? Great, I'm happy to see that. JSF has a front controller called Faces servlet, and the specification says that it operates in basically two modes. One mode is if it's a resource request, then just serve up the resource, like the style sheets and images. Or if it's not a resource request, do the regular request processing lifecycle here. That hasn't had to change in order to do server push, thankfully. So it was kind of a drop-in replacement. The only change I had to make was in this external context. External context is a JSF class that is an abstraction for things like the request and the response. So it lets the JSF API be separated from the underlying servlet API, and also allows another technology called portlet. Has anyone used or heard of portlets? Excellent. Some portlets, that's where the external context abstraction comes in. So it has a method called encode resource URL, and this method is specified to be called whenever the markup is a resource that's to be rendered. So an image tag or a style sheet or JavaScript or whatever you have. Encode resource URL is going to be called. So that's my hook-in point for where I can say, oh, well, I'm going to try to push this thing. So let's take a look at how that is in the demo. And I hope the screen can hold up here. That's awful small. But anyhow, let's, I can zoom in. Okay, so this is the encode resource URL, and I'm using Jetty because they're the furthest along with what their API offers. So I've set a breakpoint here in encode resource URL, and then I have a simple JSF web page that actually uses an image map. And I was trying different approaches to see if I could demonstrate a performance boost when comparing H2 to non-H2. So I wanted to see if I put enough bytes in front of the actual resource image or resource requests, if it would cause the TCP congestion window to be exceeded and thus be a little slower. but I never quite got that working. It doesn't seem to, at least on my local server, be easy to demonstrate a difference. So this resource, this page is just using image sharding, splitting the image up into multiple squares to render. But it's using the JSF 2.0 resource library syntax. So here it says we have a library called split02, and in there you have a number of these images that are split. Okay, so how does that look when we demo it? So let's clear the cache. Clear. And reload the page. Well, let me turn off, I'm not attached to debugger yet, so that's good. Let's load this. And you didn't really see that there was any kind of image tiling going on there. Let's take a look at Firebug then. Is this really HTTP2? So Tools, Web Developer, Firebug, open Firebug, and choose the network panel. And let's try again. Clear the cache and load this. Okay. And now we see the requests being delivered. And let's take a look at each individual one. And you can see it is working HTTP2. That's what this X Firefox Speedy header is. That indicates that it's being served over HTTP2. So now we can turn on our debugger and see how this looks in practice. Load the page again. Oops. Wait. I don't want the cache, that's for sure, because I've turned off the network. Okay. Clear. All right. Let's load this again. Okay, and we see the first image request here. So this is part 1 of 1. And if we go now, what are we at here? We continue part 1, 2. So this is we're just casting the request to the Jetty request dispatcher and saying push the request. So we were able to support push with just a couple lines of change in the specification, in the implementation rather. So that's kind of handy. Yes, Keto.
When you actually do the push request, is it doing a promise or is it actually?
Well, it's doing, first it must do a push promise, and then it does the push of the actual data. So yes. Hmm?
It ignores the client?
If the client doesn't have support HTTP2, then that's a no-op.
Oh, yeah, exactly.
Right.
I mean, once you establish what that.
Once you're in a push, you've already established protocol.
Right.
And I don't know if you've looked at page speed plugin to Chrome, but that makes what you're doing right now a lot easier. I mean, I got love for Firebug as well, but
Right.
I'm just saying page speed, when you plug that into Chrome, it shows you things that you've optimized and doing right, and it shows you things
Oh,
for
cool.
improvement, and
Okay.
it'll definitely show you your HTTP2 and all that.
I'll check that out. Yeah, I'm going to put a note down there for that. Page speed Chrome plugin, right? All right. Page speed Chrome plugin. Okay. All right, we've got 10 minutes left. I think we can cover the Java SE stuff. All right, this is exciting because there's a lot, I don't know, SE9, the thing I'm most looking forward to in SE9, of course, is Jigsaw, finally. It's been a long time coming. Another great feature, though, is the HTTP support. It's done with JEP 110, so you can see the JEP request on OpenJDK. The idea is to have an easy-to-use API that covers only the most common use cases, has support for both 1.1 and 2, and it's kind of fun to look at the API because it builds on Java classes going back to since 1.2, you know, the Authenticator class, for example, which is used heavily in this thing. It's important to also note that we're not necessarily trying to obsolete Apache HTTP client. Although I must say, after looking at this API, I don't see why you would still want to use it. Any Apache HTTP client fans out there? Okay, that's usually the reaction. Another fun thing to note is this is the first time in forever that we've actually done, something with the low-level network APIs. HTTP URL connection, which this API does not touch, but that's the most recent time we've done network HTTP kind of stuff. Anyone remember the hot Java browser? Yeah. So that was, when they thought that browsers would all be written in Java, which I still think is a good idea, I think it's even more compelling with this nice API. Okay, the deal is you have this HTTP client.builder. They're using the builder idiom quite heavily. And the HTTP client builder produces an HTTP client. And the HTTP client is the thing that produces one or more requests. But it does so first by producing a request builder, and then you use the request builder to produce your multiple requests coming out of that. So here's one for get, and then it produces another one for post, and so on. So it's just a handful of classes. The HTTP client is, as I said, built by the builder, and it holds information for creating one or more requests. So there is where you specify things that are going to be the same for any number of requests. Whether or not you should even try to ask the server for HTTP2. That's one of the settings they have there. Then you have HTTP request built by request builder. And the request builder is where you specify what the methods are and such, put, post, and so on. There's also a HTTP response class. And then they have this notion of body processors. So these are basically interfaces that, for which there are standard implementations that you pass to the API to do different things with the either request body or the response body. They can operate in a blocking mode where the calling thread owns the communication and whatever blocking may happen there. Or there's also a non-blocking mode that makes full use of the executor service. You could pass an executor service to the API, which gives you, of course, a ton of options for concurrency. And it uses the completable future API, which is a new thing in Java SE8. And it also makes great use of lambdas, which I hope everyone went to Venkat's talk. I didn't get to go to it, but it certainly gives a good talk on lambda. And it does have full support for server push also. I don't have a code example for that, though. So here's the basic API. You notice I'm not showing builders here because there are convenience methods that implicitly create one. So here we say HTTP request.create, pass in the new URI, and then we say send. And we pass in this thing that says there is no request body to be processing. So the nice thing about this send here is you pass it basically a callback that will be called to allow you to give the request body to the client as it sends it up to the server. So here we're saying we take the response, and I would like you to give me the body response, and the HTTP response body processor is the thing that gets called to process the response and form it in some specific way. And here there's pretty much the most common one, which is to give me the response body as a string. That's the simplest usage of the API that you'll see. A more complex example, this shows blocking. So here we're doing request create, again to foo.com. We're setting the method of get, and we're just setting that request. And note, send, that's where the rubber hits the road. That's when the bytes actually start to go out on the network pipe. So we're getting the response body as the string. Then we're getting, this is great, 5 minutes left. We're doing another request to the same server, again with get. And here we're we're just asking for the response code. And here we're capturing the body and saving it as a file. So here's another response processor. HTTP response as file. So it lets you take the response bytes and put them right to a file. Now we're doing a post request. Here we're seeing post, send, and we're putting the post body right there as a series of name-value pairs separated by comma. And then we're getting that response body. The final example I'll show is the async support. And all of these code samples, I'll give a debt of gratitude to Michael McMahon from the Java SE team in Dublin, Ireland. And he's going to be, I expect, talking about this at Java 1, I hope. If he isn't, someone else will, maybe me. I don't know. But this shows async support. And it makes use of completable future. So we have an array of futures here. And we have the same base URI. And we have another URI that we're just calling final result. So what this example does is it sends a few requests to this guy, and then it sends another one to this guy. So for each of the three file names, foo, bar, and blah, we are creating a new URI by resolving against the base URI, and then we're issuing a GET request. So note the difference here, we're saying send async. So that means don't block. And they're not shown here because it's using the implicit one, but there is an executor service that is automatically used if you don't provide one for this. I don't know what the executor service is, which of the many executor services it uses. That would be something to research more. So we do those three requests, again with send async, and then here's a little bit of lambda. Then apply response body, and we're saving it as a file. Then we say set up a dependent request upon completion of all of the above. So we use completablefuture.allof, taking the array of futures. And what that means is don't take any action until all of the others have returned. And once they've all returned, then we do this follow-on post request. So again, because we've done nothing but send async, we've done no blocking yet. So again, you can probably wear the We Are Reactive banner up to this point. No blocking has occurred, and the initial requests are in progress. Here is where we do block, last.join. So this is the fork join framework, I guess, in action. Wait for all work to complete, and then we print the response out. There are some other features here. There's going to be an ALPN implementation in Java SE 9, and I have been assured that it will be made available in some way so that you can run it on SE 8 as well. But the problem is SE 8 is done. We're not going to be adding any new API to SE 8, although we do realize that a lot of people are going to want to do ALPN on SE 8. And this is important for us because in servlet land, Java EE 8 does not depend on Java SE 9. It depends on Java SE 8. So if we're going to make use of any of this code, it has to somehow be able to be run on SE 8. So that's going to be a challenge to negotiate that. Okay? So we got 2 minutes left. Let's do the summary. The idea is Servlet 4 brings HTTP 2 to Java EE. It's a 100% compliant implementation of HTTP 2. The idea is to expose just the key features of the API: server push, stream prioritization, request response multiplexing. As far as the HTTP 2 spec goes, it was submit to the proposed standard in December. January, they handed it off to the RFC editor. And so it's still with the RFC editor. So sometime this month, we expect it'll be done as an RFC. Servlet 4 was formed in September of 2014. And we're planning to have some kind of basic early draft sometime in Q2. If you'd like to get involved, I'll leave these links up. Actually, I'll show the final safe harbor statement, and then I will leave these links up. And I will thank you for your time.